In this video, what we want to look at is a little bit more practice with synthesis or evaluating a reaction. So we've got our list of things that I've suggested that you evaluate, and we're going to try and look through a couple different examples at each of these stages and think through that process and hopefully get at it. Which is why I'm going to have the video pause here so that you can review what these statements actually say. And with that, we can go ahead and continue on. So if we're being asked for this particular synthesis, so in this case, we aren't being asked what are the steps, we're being asked what the product is. So arguably this kind of a synthesis for a lot of students is easier because you don't have to recall reagents, you just have to recall what they do. So in starting this, we need to evaluate the chemistry that's available to us. So what chemistry do we see as we move through this? Well, the first place to go would be looking at the organic structure. And in that organic structure, we see that we have this nonpolar pi bond, also known as an alkene. And that alkene, as a nonpolar pi bond, has electrons, which means we're looking at a nucleophile or a base. So those would be kind of the primary chemistries associated with that functional group. So then the next part would be, well, what is it reacting with? Because we've already identified it as a nucleophile or a base, we should be looking for either an electrophile or an acid. The first thing that we see above the arrow is Cl2. So we could draw out the Lewis structure to help us with this. And hopefully we remember that our halogens, because they are connected to an electron withdrawing group, that we do have a partial positive and therefore a decent electrophile. Before we get too excited and say we found something, we should just use it, we should also evaluate the other species underneath. This could just be a solvent. It could also be a reagent, so it is helpful to at least identify it. Hopefully we've seen water again enough that we can acknowledge that it is both acidic through the hydrogen and nucleophilic or basic through the oxygen. Okay? So if we go back to our alkene, we do have that potential for an acid-base reaction because we have the acidic hydrogen. But we have to remember, because it is a non-polar pi bond, it's not acidic enough. We have to be looking at a strong acid to activate it, which means the reaction we're going to be running is between the alkene and our electrophile. That's going to kick off the cascade for our reaction. When we go through and do that, we do have to realize a couple things. There are two places where that chlorine could go. So we have to consider where it should balance out. Again, a lot of that's going to come from the regiochemistry of recognizing something about the resonance within this. We would expect the negative charge and the positive charge to go on the more substituted, which means the chlorine, being our electrophile, should actually connect out here. This would leave a positive charge on the inside, which isn't so great, except that chlorine fits that pattern. If we think back to our electrophilic reagents way, way long ago, it also has that lone pair it can immediately hook up, which means we aren't actually seeing the formation of a carbocation, we're seeing the formation of this goofy three-membered ring. Okay? With a chloronium ion. That chlorine, yes, is exceptionally unstable, and that ring definitely wants to break open. Okay? But there is evidence to suggest that that ring has some existence, right? Which means we need a nucleophile to come in and break it. So now we could go back and look at our solution to see what we have for nucleophiles. We do have the chloride. We also still have the nucleophilic water. This is one that ultimately reagent memorization is going to come in to help out. Water is in there in a vast excess as the solvent and is going to be the most likely one to go through an attack. Because we have a great leaving group, that chlorine does not want to be positive, and we have a weak nucleophile, because it is not charged, our water is going to attack the more substituted position, causing the bond to break. And what we would get would be our OH, and I'm going to show it as like that, and then our chlorine connected. water from solution. Remember, it's slightly basic. Can pick up that hydrogen. We'll use a black arrow for this. And that would get us to the product of our very first step. Okay? And if we think through this, we just did a mechanism for one part of this reaction. That's a lot of work. If you've memorized what the reagents are, you can jump to that final answer a little bit quicker. But if you also just accept outright that you need to draw how the reaction's working, you can draw all of this relatively quickly and nail down one of the big conclusions. These are stereocenters. Because they are stereocenters, we would need to specify our wedges and dashes. Because we've got our mechanism drawn out, we can see that the chlorine could have attacked from either side, but that ring must be the same. The OH has to come in and attack from the back side, which means in our end result, we know those two were added on opposite sides. We get the trans product. That becomes relevant. Yeah, let's just say relevant. In the next step, where we can throw in sodium hydroxide. Hydroxide, as soon as you see that metal, I would recommend personally crossing it out, putting in the negative charge on our oxygen. That could act as a nucleophile or a base. Okay. If it acts as a nucleophile, we would just get a substitution reaction, which isn't all that big of a deal, and it's possible. But acid-base chemistry should be considered before we start doing nucleophilic substitution. And we do have an acidic hydrogen on that oxygen. This is going to generate our alkoxide, so our alkyl structure with a negative charge on an oxygen. We have the perfect alignment of dashed and wedged. This can do a backside attack, kick that out. That looks suspiciously like a positive charge. Let's fix that. And what we get out of that result is an epoxide. One of the other things, as I'm drawing on this stereochemistry, it makes me recognize that I do have to acknowledge that I get an enantiomer. That enantiomer is because that chlorine could have attacked or been attacked where it was above the alkene or below. So we're still getting that plus enantiomer pretty much all the way through this. I'm not even going to write that out because I bollocks the spelling. So now we move on to step 3. And we'd have to identify our reactivity. One of the things that might be triggering us is that we still have a pretty good electrophile in our carbons, because that's a 3-membered ring, so we get ring strain on that. And then we'd have to look for our potential nucleophile in that starting material. This is where it pays dividends to know what some of our simplifications are. Remember that TS? That TS meant this structure. And if we connected it to OH as our squiggle, that approximated H2SO4. That is a stupidly strong acid. So really, I don't care about anything else. The acid-base chemistry is going to happen first. And we're going to protonate. With that epoxide now protonated, it is dying to bust open. So something's going to have to pop that open. That's where we can get the lone pair electrons from the oxygen of our CH3OH. The TSOH, those electrons are tied up in resonance and therefore not nucleophilic. So we're now looking at our methanol coming in. Backside attack, it's going to attack the most substituted side because we have that very good leaving group with our alcohol. And we would get, whoops, as I started to draw too many carbons, the OH connected out there. The CH3OH had to come in from the backside, which means it's going to have to become wedged. OCH3. There's the methyl. Officially, we have that hydrogen still on there from our alcohol. This is where another equivalent of alcohol can come in, finalize, remove that, and we would end with our final product. I would bet that if this showed up, you aren't going to see it without stereochemistry. You would have to know all the wedges and dashes appropriately. And because some of those change through the course of the mechanism that we've drawn out here, it's going to become tricky, and you're going to see an awful lot of different pairings behind that. Okay? So, behind our synthesis, we're thinking about where's that chemistry at each time. Note lots of labeling of bases, nucleophiles, electrophiles, and acids. I didn't actually call out the chemical reactions behind these, but we've got an electrophilic addition running in that first cycle, followed by an acid base, followed by a substitution, followed by an acid base, and yet another substitution. If we can recognize those patterns, it can help us move through this. Yes, that was a lot, and it requires a bit of practice to get used to, but I have every confidence that you can go through and do it with practice. To that end, ta-da, we can look at some practice. Okay, so I would like you to take a second, hit the pause button, and work through some of these. That would be now, that space bar. Go ahead and do it. Okay, in theory, I'm going to assume you've now had some time to practice and look at these. Because it could take up some space here, what I want to go through and do is delete one of these and only focus it one at a time. Okay, this first one is technically a synthesis or multi-step. Lots of stuff is happening in an individual reaction, so we might see a whole bunch of different things going on, or it could be relatively simple. Things that jump out were a carboxylic acid. We have an electrophilic Br2. We got that water again, which is potentially nucleophilic or basic, and potentially acidic. And then PBr3. This would be a reagent that I would say should go on a memorization list so that you don't have to think about it. And this memory list should be that you can convert an OH to a bromide. So as soon as we see that PBr3, that should be our big trigger, because that's going to change a lot of the chemistry. We won't have that acidic OH anymore. And of course, there's a crap ton of carbons in here. One, I think I've got that right. And then we'd have the Br. We can't bring in the nucleophilic or basic or acidic water yet, because we haven't addressed what that Br2 is doing. If we think back to our reagent with PBr3, Br2 wasn't really necessary. Okay, so why is that Br2 there? Well, we have seen Br2 act as an electrophile, but that would require a nucleophile. I don't see anything obviously nucleophilic here, unless, say, a carbon to hydrogen bond was located next to a carbonyl that would allow for resonance. Oh, if that was the case, we could generate the structure. And of course I drew too many bonds. Double bond, negative charge. And that would have resonance where we could put a negative charge on that carbon. That becomes super useful because that is now a great nucleophile that could react with our bromine. This will set us up with this intermediate structure. Okay? And we've now done effectively a double substitution. Two reagents that did different things got tossed in at the exact same time. Okay, and of course my internet is flaking out on me, which makes this recording a little bit more challenging, but hopefully we're still good. Which then means we would move to the next step with our acidic water, nucleophilic or basic. There isn't anything particularly basic in our structure. okay, at this point. Okay, so nothing basic to look at. Is there anything particularly acidic? Not really. Is there anything particularly electrophilic? Okay, well, there is this carbon that is connected to an oxygen that is electron withdrawing and a bromine that is electron withdrawing. That seems reasonable. So let's have the electrons of our oxygen come in and attack there. This chemistry is officially beyond the scope of this unit. It's actually going to show up in 2 units because what we're about to do is what's known as a nucleophilic addition followed by an elimination. The weakest bond would be that pi bond. The pi bond breaks open first and foremost. That sets us up with our addition. We would have a negative oxygen, which is not particularly stable, and a positive water. A base could come along, anything remotely basic, deprotonate that so that we're set a little bit better. The oxygen electrons can come back down and now kick out bromide as a really good leaving group. Okay, why would that leaving group be so great? Well, bromide is large. And what do we have? We now have the bromine connected and the OH. For those of you keeping score, what we've done beginning to end is just a substitution, a hydrogen for the bromine. So one might ask, why didn't I just do that from the very beginning? Okay, this becomes one of the tricky functional differences between a carboxylic acid and an acyl halide. The alpha position on the carboxylic acid is not particularly acidic because, well, there's a more acidic hydrogen. When we look at the acyl halide, that hydrogen, that alpha hydrogen, becomes actually more acidic because that bromine withdraws electrons. The oxygen in the carboxylic acid actually donates electrons via resonance. So by converting it to the alkyl or the acyl bromide, we actually facilitate the substitution reaction we want. Okay, kind of a neat little reaction. Again, a bit on the more advanced side. Don't stress if you got it wrong. Try and figure out where things went wrong and poke at that chemistry. Okay, the next one that we had on this list, okay, acidic conditions, which should be a giant red flag that's where we're going to start. It's actually showing H plus as an active intermediate. So let's go ahead and tag that right away. We're going to have that positive oxygen, which is not going to like it, and it's going to want to resonate. That resonance forms an unstable carbocation that we're going to want to stabilize somehow, and we can stabilize that through the formation of an enol. The tricky thing here is that there are 2 positions to address, a purple position and a blue position. Whoops, and we're missing the carbocation. Because of the conditions that we're under acidic conditions, we're going to end up pushing for the more thermodynamically stable product, which means we're going to want the more substituted position. We're going to want to form the elimination or the enol in this fashion. Okay? And a lot of that has to do with the conditions we're under. If we were under an exceptionally basic environment, we need to neutralize that base as fast as possible. So we'll pull from the more or the less sterically hindered side. Because we're under an acidic environment, I've already neutralized all the active species. I'm going to pull in such a fashion to make the most stable product. A lot of people might say, well, what base was used to remove that? I don't really care as long as I can acknowledge that it's a weak base, not negatively charged. Okay? And you might say, well, if there's no base, then it shouldn't do this. And you're right. It doesn't do this in very high amounts. And in fact, it largely favors the keto form. Okay? And we addressed this when we talked about our keto enols. But what happens is a small amount forms here. That small amount can now undergo a reaction that stabilizes the electrophilicity of that bromine. And we would end up putting a negative charge on that bromide. So we get a really good leaving group. Okay? That's a pretty sweet system. Okay? That's what drives this reaction, is that this step is the determiner. It's the rate limiting step that pushes this reaction forwards. Okay? At this point, we could go through and say that we just do a workup of the reaction. That workup is going to take care of that hydrogen, and we would get our keto form. We could probably also go through and say that this workup is actually step 2 and adding the pyridine. We might have to add a little bit more pyridine, which is probably why we would do the workup instead, because pyridine is highly toxic. And pyridine, if you remember from earlier videos, had that lone pair. That lone pair that was basic. Why is that important? Well, what kind of reaction would follow under a basic system? Eliminations. Where is there a hydrogen to eliminate? We actually have hydrogens here. That base can come in. I wanted to remove the other one and do an elimination of that bromine. Yes, we could have done something on the enolate side with those hydrogens. So why does it make sense to go with the red hydrogen instead of the blue? That's conjugation. That's resonance. That increased resonance stabilizes the overall structure, and that's really what drives this reaction forwards. Okay. So with that, we've got 2 more practices. These are a little bit more strict along synthesis. You have to identify all of your individual pieces here, and then you would want to try to predict how to get there. So here you're being asked to come up with the reagents. What makes this one a little bit trickier is that I'm going to add the rule that you can't use any other carbon source. Sorry, that's a no. Okay, so with no other carbon source, we'd have to compare reactant to product to decide what's going on. Reactant starts with 3, product ends with 6. Well, hopefully that allows you to see that to get those 6, we need 2 3s. We would need 2 starting materials. Okay, so we're going to end up using that molecule in 2 different pathways and somehow hook them up. Now we should identify the chemistries. Well, our starting position, where that bromine is active. If we look at the next one, okay, lots of activities. Okay, I know I'm going to have to run 2 of these pieces, so let's split through the middle and assume I now have 2 paths. Which path do I want to look at? Green path or the purple path? I'm going to have to do both, but we'll pick whichever one we want to start with and see where we can get. Okay, so with that, I'm just going to continue on and try and draw it out as fast as I can so that you can get through this video quicker. Yeah, dang. So, yeah, ignore that. So if we go through, let's take a look at the purple path first. I need to somehow convert the bromide into this kind of structure. So I need a double bond in there. And yes, for the moment, I'm ignoring that oxygen. So if I evaluate that difference, chemistry has moved. Okay. In the starting structure, it's only at the terminal or the internal carbon, and it needs to at very least make it out to one end. Okay, so how can I get the electrons to go out to that spot? Okay, I would need some kind of pi bond. And elimination would be a good way to get that chemistry to move. So if I ran an elimination, that would get me the double bond there. I do now have a consideration. I could try and put the oxygen on the purple piece, or I could put it on the green piece. Okay, I'm going to argue that it's going to be easier to get it on the purple piece. Okay, and a lot of that comes from, well, unfortunately, me knowing a little bit more about steps ahead. So we're looking at those substitutions, okay, or those steps. How can I get chemistry out there? Well, if I notice that black carbon is allylic to the pi bond, the allylic position is extra susceptible to a radical substitution. Shouldn't be calling it radical SN because the N is nucleophile. That radical substitution could put on a bromine. I could then follow that up with, this was all supposed to be purple, another substitution where I try and make that an OH. Okay, how would I go through and do that? Well, primary, I'm probably going to pop on a hydroxide because that's a primary substrate. I want an SN2 mechanism. Okay, so hydroxide's probably a good call for that. The hydroxide's probably not going to interact with the pi bond because the pi bond is also a nucleophile. To do the radical substitution, I need to do Br or find a bromine source. I could use Br2 and light. There are problems with that one, so I could also use NBS, which tends to be a little bit better at this, and light. The elimination itself, to get that elimination to occur, it doesn't really matter here. I'm going to push heat, and hydroxide would probably be enough to get this to go. Just a standard sodium hydroxide. This gets me that oxygen connected on there, which means on the green side, I just need to convert this bromine out to a somehow active position here. Because I know my oxygen over here is going to be my nucleophile, I know this needs to be an electrophile. So I need a halogen out there. So how can I go through and do that? Again, the chemistry has moved, which means I'm going to have to run an elimination. Once I've done the elimination, I could now do an addition to get my bromine out there. All I'm adding is H and Br, so there we go. Complication, that would place the bromine right back where I didn't want it to be. So I want the bromine to go to a position that it does not want to be. That's going to be radical ROR. This will now get me the chemistry with that bromine on there. I now have an alkyl halide and an alcohol that if I mix the alcohol with a strong base and then add the alkyl halide, I would then get my final product, which was an ether. That particular step would be known as a Williamson ether synthesis. Okay. Again, lots of moving pieces, but what we're trying to do is run simple reactions to transition from one place to the next. Okay. And the last one is going to be extra challenging because the very last step we have not discussed at all this semester. So I don't expect you to get a reagent, but I do expect you to be able to get a reaction type. Okay. So I'm just going to blanket kind of walk through the type of systems that you should be getting here. We need to be doing a radical substitution, okay, followed by a Hofmann elimination. Shouldn't have said that. That was probably more information than it needed to be. A Hofmann elimination followed by the addition. I'm just going to say an addition. And then this last step is the kind of questionable one. And that's going to be kind of the hardest. So what I'm going to do, still haven't decided if I want to make this a quiz or not. I'm going to say not. And that step is going to be challenging because what you will have will be right here. If you did everything correctly, that's where you should end. Okay. How do we go through and do that? Well, what I want you to be able to acknowledge is that the change is that you are losing hydrogens. The loss of hydrogens is a red flag for oxidation. And so what you should acknowledge is that while you don't know the reagent there, you need to do an oxidation reaction. Okay? And that would be more than enough or more than sufficient for what I want on this particular one. This just happened to be kind of a holdover from a different timing of the particular content. Okay, so with that, I've already talked, as far as I'm concerned, way too much. If you have questions about the particular reagents that shift these, or if I made a mistake in those sequences, please feel free to contact me. More than happy to discuss out these individual syntheses. These are intended to be a little bit more simple than some of the more advanced ones that you may see in your career. And so with that, we will go ahead and stop the video. Thanks for listening.